Hello, my name is Jonathan Zabalaga, and I am a PhD student at the Technical University of Munich. Today, I'll be presenting some recent research of ours on differentiable collision-free parametric corridors. This is a joint project with my advisors Zachary Manchester and Marcus Rill. Our motivation comes from the agile navigation of autonomous and robotic systems. In the last few years, we have seen immense progress towards this direction. Autonomous drones have been able to beat human expert pilots in drone racing. For the first time, we have seen autonomous Formula cars racing head-to-head, and legged systems such as humanoids have shown parkour skills way beyond an average human being. Looking into this scenario, one might feel like there is not much more to do when it comes to robotic agility. However, taking a step back, it becomes apparent that all these demonstrations have been tailored to highly controlled environments, and as soon as we try to apply them in the real world, things start to fall apart. This lack of versatility and robustness is the reason why the agile behaviors are not applicable in the wild, a crucial transition for the widespread adoption of robotics into our society. Motivated by this scenario, in this work, we aim to close this gap by presenting a method that enforces safety without compromising agility. In particular, we present a corridor generation method that solely requires a point cloud and a reference path to obtain corridors that are collision-free, path-parametric, and differentiable with real-time computations. To better understand the implications of these four attributes, let's explain each of them. First, we want the corridors to be collision-free for the obvious reasons of enforcing safety. Second, we define the corridors as path-parametric so that they are compliant with existing control algorithms such as contouring control or progress maximization. Third, we require the corridors to be differentiable in order to ensure that they are compatible with optimization and learning-based navigation algorithms. Last but not least, being able to compute the corridors in real time is crucial for ensuring that they are deployable in real-world autonomous systems. To achieve this, our method relies on three main ingredients. First, we choose to represent the obstacle-free space as a corridor whose cross-section is given by an off-centered ellipse. Second, we parameterize this ellipse by Chebyshev polynomials, allowing us to sweep along the reference path. Third, in order to compute the coefficients associated with these polynomials, we formulate a convex optimization problem that maximizes the volume of the corridor within the collision-free space. In the upcoming slides, we proceed to provide further details about each of these three blocks. Our corridors consist of a predefined cross-section that sweeps the parametric path given by the user. In this first ingredient of our method, we choose the shape of this cross-section. When doing so, our objective is to select a cross-section that offers maximum adaptability to the obstacle-free space while ensuring differentiability and computational feasibility. The simplest approach is a circle, which offers a single degree of freedom. An ellipse increases this number to 3, and allowing it to have an offset from the reference path further raises this total degrees of freedom to 5. Beyond the circular or the elliptical choices, there are more elaborate options, such as polyhedrons or semi-algebraic sets. However, these cross-sections cannot guarantee to remain differentiable or closed throughout the entire corridor. For this reason, we pick the most favorable option within the feasible ones, a rotating off-centered ellipse. Mathematically, this is defined by the matrix E and the offset P sub E, and its equation is given inside the red box. Having defined the cross-section as a rotating off-centered ellipse, the next step is to parameterize it, so that it sweeps the reference path from the beginning to the end. This implies that the ellipse, and thereby the matrix E and the offset PE, evolve according to path parameter Xi. For this purpose, we choose to parameterize these variables with Chebyshev polynomials. There are two reasons behind this decision. Firstly, utilizing polynomials ensures that the resulting corridors exhibit inherent smoothness and differentiability. Secondly, the Chebyshev basis guarantees that our method is numerically stable, even for high polynomial degrees. Intuitively, increasing the degree of the polynomial enhances the corridor's ability to adapt to variations along the reference path. From these decisions, it follows that the corridor's shape and size is exclusively dependent on the polynomial coefficients highlighted in yellow. This naturally leads to the following question: how can we compute the coefficients? Well, to answer that, we need to move into the third and final ingredient of our methodology. From the available collision-free corridors, we aim to identify the one with the largest volume. To determine the coefficients of this corridor, we formulate an optimization problem that maximizes the volume, ensuring that the ellipse matrix E remains positive definite throughout the corridor and that all points in the point cloud lie outside of it. To make this problem computationally tractable, we conduct the following approximations. Firstly, we discretize the continuous parts of the optimization problem into n evaluations. Secondly, we avoid the nonlinearities associated with the determinant of the ellipse by approximating it with a trace. Thirdly, we introduce a wrapper around the reference path, ensuring that the problem always remains bounded. By incorporating all three modifications, the original problem becomes a convex optimization problem. More specifically, it is a semi-definite program. Despite being a convex problem, SDPs are the most difficult convex problems to solve. To overcome this burden, we replace the linear matrix inequality highlighted in purple with the diagonal dominance. This approximation converts the SDP into a linear program. LPs are very well understood and extremely lightweight, and therefore can be very efficiently solved with off-the-shelf solvers. As a final remark, notice that in the planar case, there is no need for the diagonal dominance approximation, since the original problem is already an LP. To evaluate our approach, we split the experimental analysis into two parts. In this slide, we will focus in the first part, where we test our corridor generation method in a synthetic environment created by randomly positioning a series of columns and rings. We begin by comparing the size of the corridors obtained for various polynomial degrees. The corridors obtained for degrees 3 and 15 are depicted by the animations in blue and green. From these results, it is apparent that increasing the degree of the polynomial enhances the corridor's expressiveness. The blue is the smallest corridor, while the green shows an increased capacity to adapt to the environment, resulting in a larger corridor. The plot in the right side validates this observation by demonstrating the correlation between the degree of the polynomial and the volume of the corridor. Additionally, we showcase the importance of optimizing over the offset with respect to the reference path. The figure at the lower part of the slide demonstrates that constraining the ellipse to be attached to the reference path limits the achievable maximum volume, which is especially detrimental when the reference path is close to the obstacles. In the second part of the experiments, we studied the method's applicability to a real-world autonomous driving scenario. In particular, we focus on a roundabout intersection that allows for the computation of two corridors. In here, our analysis consists of two parts. First, to illustrate how our method compares to the well-established convex decomposition, we refer to the figure at the top right side of the slide. It shows the top views of the corridors generated for different polynomial degrees n and numbers of convex sets P. In contrast to the discrete nature of convex decomposition, our approach yields a continuous and smooth representation of space. Second, to gain a better understanding of the consequences for approximating the SDP into an LP, we refer to the figure at the lower right side. Here, we show the volumes and solve times obtained from computing the pink corridor for various polynomial degrees. These results indicate that the LP relaxation yields exactly the same corridor volumes as the original SDP, while showing major computational speedups. To sum up, in this talk, we have presented a method that to compute corridors that are collision-free, path-parametric, and differentiable with real-time capabilities. To achieve this, we have relied on three main ingredients. First, we have modeled the cross-section of the corridor as an off-centered ellipse. Second, we have parametrized the corridor with Chebyshev polynomials. And third, we have formulated a convex optimization problem capable of maximizing the corridor's volume. To evaluate our method, we have conducted experiments in synthetic and real-world cases. In both instances, we have observed that, as expected, a higher polynomial degree correlates to an increased corridor volume. We have also concluded that allowing the corridor to have an offset with respect to the reference path plays a crucial role. Additionally, by benchmarking against convex decomposition, we have shown how our method yields continuous and smooth space representations. Last but not least, our numerical evaluations indicate that the LP approximation provides the same corridors as the original SDP, while offering substantial computational speedups. For further details, please check the paper on arXiv or download the code from GitHub. Thank you very much for your attention.